Okay, so gives me pleasure to introduce Professor Francesc Castella from University of California in Santa Barbara, and he'll give the final lecture of his course on Iwasawa theory for elliptic curves at Eisenstein primes.
Thanks very much for the introduction. Yeah, so let me remind you of the setting that we're in. So E is an elliptical probability rationals of conductor N. And then we're considering P and odd Eisenstein prime. So the P torsion is reducible as a Galois module. So I can write its semi-simplification as a sum of two characters that I'm denoting phi and psi. And we know the product is omega. Okay, so we have this relation over here. And then yesterday, we spent the entire lecture proving this theorem that I call Theorem A, saying that if this character at P is different from 1 or omega, and K is an imaginary quadratic field satisfying the Herbner hypothesis and such that P splits in K, then what we call the VDP main conjecture in the first talk holds. Okay, so this thermal group is lambda torsion, and we have this equality of characteristic ideals. Again, I remind you of some of the notation. So this lambda minus denotes the anti-cyclotomic Iwasawa algebra. And here we are taking this scalar extension, this base extension, because that's where this VDP p-adical function is, pretty much like Descartes' p-adical function. Okay, so that was a quick summary from yesterday. And as I mentioned at the very end, so a weak form of this theorem that was enough for some hypothesis, for some applications, was joint work also with Jai-Hun Lee. But this stronger form will be actually a key ingredient in the proof of Mazur's cyclotomic main conjecture that I hope to explain today. Okay, so today's goal is the following. I'll call it Theorem B. So we've also joined with Jella Grossi and Chris Skinner. Okay, so we're going to make the same hypothesis on our character. Phi restricted to a decomposition group at P should not be 1 or omega. Okay, and then we get what Mazur's main conjecture predicts. Okay, so then the usual thermal group over the cyclotomic ZP extension is lambda torsion. And the characteristic ideal being generated by the Mazur and Swinnerton-Dyer p-adical function. Okay, so hence Mazur's main conjecture. Okay, for this Eisenstein prime speed. Okay, in the first lecture, I already, or rather at the beginning of the second, I already mentioned that what's known in the non-Eisenstein case. Okay, but let me now tell you about previous results that were known in the Eisenstein case for this conjecture, because some of it will be we're going to be building on that. Okay, so some previous results on Mazur's main conjecture for Eisenstein primes. Okay, so the first name I should mention here is Carl Rubin, who proved it in the CM case. Okay, then there is Kado's work, which in this case of Eisenstein prime still gives us 1 divisibility after inverting P. Okay, so he showed that X is lambda torsion. With the predicted divisibility, well, one of the predicted divisibilities after inverting P. So in lambda 1 over P. So that was in the early 2000s, so at least it was published then. And then about 10 years later, Chris Ruthridge did a refinement of Kado's work that will be useful for us. So Ruthridge, what he showed is that in this Eisenstein case, the Mazur and Newton-Dyer p-adical function is actually integral. Okay, so LP Q over Q is in lambda. Remember that out of the construction by Mazur and Newton-Dyer, all we knew was that it was in lambda. It had bounded denominators, but it could just be in lambda tensor QP. Okay, and moreover, from that he deduced that this divisibility of Kados is actually holds integrally. Okay, so about divisibility. Divisibility. Holds in lambda. Okay, and the next, well, not historically the next, but the next I'm going to mention is Greenberg-Barzal. Who obtained a proof of Mazur's main conjecture for Eisenstein primes in roughly half of the cases. Okay, so proof for half of the cases. Okay, so more precisely, they had to make some hypotheses on this character phi that I'm denoting. Okay, so they needed phi to be either unramified at P and not, or ramified and P and even. And the reason why they needed this condition is that under this hypothesis, it follows from the work of Mazur and Wiles and Ferrero-Washington that this p-adical function of has vanishing mean value. So this hypothesis implies by Mazur, Wiles, and Ferrero-Washington it implies that both the algebraic and the mu invariant of in this setting they are zero. Algebraic and analytical mu invariant. Okay. So in fact, in this work, they introduce what we called yesterday the Greenberg-Barzal method. That yesterday we explained its extension to the anticyclotomic setting. And in some sense, the anticyclotomic setting is better behaved in that case because thanks to Hida's results, we know that in our situation we have always vanishing of mu. Whereas in the cyclotomic case, that's certainly not the case. Okay, so when one is outside this situation, as I'm going to mention more in detail later, the mu invariant will be positive. Okay, so this method of Greenberg-Vatsal is not going to be useful in concluding this, proving this result. Okay, so what we're going to do to prove Theorem B was to use a different method. Okay, so that's what I want to explain. And this method actually not only will extend the result of Greenberg-Vatsal to the other half of the cases, but also will give a new proof of the half that they could handle. Okay, so we'll remark here. Okay, so our Theorem B. Also gives a new proof of Greenberg-Vatsal. Okay. So any questions so far? Okay, so if not, let me continue. Okay, so how are we going to do this? So again, we have Kato's divisibility. So one way to conclude the proof would be a way of checking that the Iwasawa invariants are the same. Okay, so that's the strategy. We're going to compare the Iwasawa invariants on both sides. Okay, so as I was saying, after Kato, the Kato's divisibility to prove the Kato's divisibility. To prove Mazur's main conjecture, it's enough to show that both the Selmer group and the p-adical function have the same Iwasawa invariant. Okay. Now, so the mu could be positive, but if we can show that they are the same, that will suffice. Okay, but as I mentioned, the Greenberg-Vatsal method allows us to handle the case where mu is 0. Okay, but in general, mu is positive. So let me say something more about this. Okay, so for instance, Greenberg has some results showing the following. Okay, so with the notations that we are using, if our character phi is ramified at P and not, okay, Okay, so you should think of this as meaning that the P torsion contains a mu types of group. Okay, so, and here, okay, so there is this. Okay, so then the mu invariant is positive. Okay, so the Selma group has positive mu. Okay, in fact, Greenberg proved something more precise. Okay, so in fact, if there exists C as a group of the P power torsion on E, which is cyclic of order P to the M, say, with GQ action ramified at P and O. Okay, so again, a mu types of group of order P to the M, then the mu invariant is at least this value. And the expectation is that in general, the value of the mu invariant of the Selma group should be the maximal such M. Okay, so that's the expected story on the algebraic side, and on the analytic side, there is the situation is completely parallel. There are some results of Stevens which are perfectly compatible. So Stevens deals with the Mason-Newton periodical function, and his estimates on the value of the mu invariant for that is they are completely compatible with Greenberg's. Okay, so Stevens has some similar results / expectation on the analytic side. Okay, so we need to do something else. Okay, so we'll use a different method. Okay, so the first thing we're going to do is we're going to choose. Okay, so we want to build on the Theorem A that I stated at the beginning, okay, which was something having to do with the anticyclotomic ZP extension. Okay, and what we're going to do is we're going to evaluate that equality of characteristic ideals in Theorem A at a certain character. Okay, so this is what I'll denote by alpha. Okay, so alpha is an anticyclotomic character valued in some finite extension of CP. This is anticyclotomic. Okay, and we want this character to be sufficiently close to 1. Okay, so, and how close will be made precise as we go along. Okay, so call bar pi the uniformizer of R, and M will be something taken sufficiently large. Okay, for now, what we ask for this alpha is to be a character at which the BDP periodical function is non-zero. Okay, so I could write E k at alpha being non-zero, but instead I want to think of this as being as twisting the p-adical function and evaluating at 0. Okay, so instead of writing this, what I'm going to write is E parentheses alpha over K evaluated at 0. Okay, so if you want, essentially I'm twisting the form associated with E by this character alpha, and this twisted p-adical function I evaluated at 0. Okay, and we want this to be non-zero. And this we can always find such alpha because we've seen that in this case we can deduce from Hida's non-vanishing results that this p-adical function is non-zero as an element in the Iwasawa object. Okay. Right. So now I can state a key input to our arguments. Okay. Okay, so this is going to be a refinement of the construction of Bennington flat classes that we saw in Antonio Lei's lectures towards the end. Okay, so this the work of Ley, Leffler service, and King's Leffler service. Okay, and this refinement, there are many people who contributed to this. So I'll mention, certainly should mention Burungale, Skinner, Tian. I'll say a few words about the refinements that are needed. Okay, also this related work of Bertolini, Darmon, and Venerucci. And we also had to do some further refinements. Okay, so what's the statement? Okay, so I need, now in this residually reducible case, it's important to specify what curve in the isogeny class we're considering. Okay, so now I'm going to tell you which curve we are taking. Okay, so we let E bullet to be the elliptic curve in the isogeny class of E. Such that we have the following. Okay, so we're going to look at the realization of the Galois representation associated to our elliptic curve, the one occurring on the open modular curve. Okay, so we look at étale cohomology of y1 of n, which change to q bar with coefficients in qp1, qp twisted 1, and then the representation associated with the p-adic representation associated with our elliptic curve that I'll denote v sub f is the maximal quotient of this h1 on which Hecke acts via the Fourier coefficients of f. Okay, so this is the maximal quotient. Where TL acts as AL of F or AL of E for all that. Okay, and now sitting inside H1, on this H1, there is a natural lattice just given by taking cohomology but with ZP coefficients. And now the image of this lattice, or this integral cohomology under this quotient, defines a natural lattice on V sub f. Okay, so I'll denote this by T sub f. And Woodridge, in that refinement of Karos that I alluded to earlier, showed that this lattice is isomorphic to the theoretical module of a certain elliptic curve that he constructed. And this is what I'm denoting U Wood. So okay, so this isomorphism over here was shown by Woodridge. Okay, so we look at this elliptic curve in the isogeny class. And so I'm going to tell you about the existence of a certain two-variable Beilinson flat class. Okay, so this will be an Iwasawa cohomology class extending over the CP square extension of our imaginary quadratic field. Okay, so then there exists a two-variable Beilinson flat class. Okay, so I'll denote it BF sub alpha. Okay, we're going to work with this alpha twist for our arguments. Okay, let me just put parentheses alpha for consistency with what I had before. Okay, so this K infinity is the CP square extension. Okay, so the picture is like this. We have K here. Then, okay, so the Galois group of entire tower, I'll denote gamma sub K, isomorphic to CP square, and there are two distinguished lines in this CP square. One is given by the anticyclotomic line, and the other by the cyclotomic. Okay, so this will denote K infinity plus, which you can identify as the compositum of Q with, sorry, K with the cyclotomic CP extension of Q. Okay, so we have this diagram, and here was what we call gamma, the cyclotomic Galois group, or the Galois group of the cyclotomic CP extension, and this is gamma minus. Okay, so there is such a class, and it's related to two different p-adical functions. Okay, so there exists such a class together with two explicit reciprocity laws. Okay, so the first one, I'll denote ERL1. Okay, so remember, P splits in our imaginary quadratic field. So when we look at the restriction at V of this BF alpha, this reciprocity law, which will be, again, applying a generalized common power series map to this class, and we'll take it to some p-adical function. The p-adical function that appears is an element I'll denote LP PR for Perrin-Riou. So that's a p-adical function I haven't introduced yet. Okay, so this is an element in this two-variable Iwasawa algebra. And it's again defined by an interpolation property. What you interpolate now are finite order twists of the L function of it. Okay, so twist by character, finite order characters of this group. Okay, and even though I'm not, I don't say more about the definition of this p-adical function. What we're going to use is that, so there is a projection map we can project this to the cyclotomic Iwasawa algebra. Okay. So to this line over here, and what we get when doing so is okay, so I'll denote this projection by LP PR, okay, with a superscript plus. Okay. If that's when alpha is 0. Sorry, when alpha is trivial. Okay, so we're going to use that this relation, this reciprocity law. We have it for any character alpha, but when we take the case where alpha is 1 and we look at the image under this projection, this will become the product of two Mazur-Newton-Dyer p-adical functions. So similarly as it happens for the classical L functions. Okay, so this will decompose as the product of two Mazur-Newton-Dyer p-adical functions. Okay. And this is really happening up to a unit. Okay, so that's the first explicit reciprocity law. There will be a second one now involving the prime V bar. Okay, so I'll call it ERL2. Okay, so now when we look at the restriction of the other prime, okay, we get a link to another two-variable p-adical function that I'll denote LV Greenberg, GR for Greenberg. Okay, so this lives in ZP unramified gamma k. Now recall our alpha is anti-cyclotomic. Okay, so now if I project to this, what I was denoting lambda tilde minus. Okay, so I'm essentially just projecting now to the anti-cyclotomic line. What I get, what you can show you get is, okay, so I'll denote this projection by a superscript minus. And what you can find is just by comparing the interpolation properties, you get the square of the BDP. Okay, I'm running out of space here. Okay. And this is up to a unit. Okay. Okay, so it's a very long statement, sorry. It took like two pages to write down completely. Okay, but I won't say much about the proof. We've already seen some of this in Antonio's lectures. But let me tell you some words about what are the refinements beyond what we have already seen. Okay, so the key ingredient is to consider Bennington flag classes as constructed in the work of Ley-Leffer-Serbs and King-Leffer-Serbs. Okay, so Bennington flag classes. So these are classes that extend over the cyclotomic ZP extension of Q. But as we've seen, they are attached to ranking server convolution of two modular forms, but we can also deform these forms in Hida families. Okay, so we consider them associated to F, the new form associated with our elliptic curve, times a certain CM Hida family. Okay, and one of the difficulties is that the CM Hida family that we need for our application doesn't satisfy the hypotheses that are needed in these previous works. Okay, so this Hida family. Okay, so this is the CM Hida family. Which is a cuspidal one, but in weight one, it specializes to a weight one Eisenstein series. Okay, so with weight one specialization given by a weight one Eisenstein series associated to the characters trivial and the quadratic character associated to K. Okay, so this CM family is bad in two ways. So first it's in weight one is Eisenstein, so it's that's one of the reasons why that's problematic. And secondly, when you look at it at P, because we're assuming that P splits in K, the locally at P is P indistinguished. Okay, so understanding the representation associated with this ranking server convolution is what requires this refinement in these works I'm mentioning here. Okay, Burungale, Skinner, Tian, and there is a related work of Bertolini, and Benerucci. And also understanding the associated reciprocity laws in this case. And now what we need to do further in order to get something that for our application is in this reciprocity law, there are certain congruence numbers that appear. And we need to kind of relate these congruence numbers to the particular curve in the isogeny class that we're picking. And that's related to certain modular degrees and so on. Okay, so that's all I'm going to say about this key ingredient in the proof. And now, why is this going to be useful? So, so the key use we're going to make of this is that it allows us to relate two different main conjectures. Okay, so maybe I can move that over here. Okay, so in particular, okay, so this gives an equivalence between three different cyclotomic main conjectures. Okay, so on the one hand, we have the Iwasawa main conjecture for this X, the classical Selmer group over K infinity plus. Okay, so this main conjecture is essentially a sum of two Mazur main conjectures, one for E and one for the quadratic twist. Okay, then on the other hand, we have, okay, so the left-hand side is what we're trying to prove. Now, the right-hand side is going to be a cyclotomic main conjecture, but ultimately, we'll be able to relate to what we proved in Theorem A. Okay, so this is an Iwasawa main conjecture. Now, for this Selmer group, where we impose no condition at one of the primes and triviality at the other, but now we are viewing it over K infinity plus. Okay, so the right-hand side is something that we'll be able to say something thanks to Theorem B. Okay, and the bridge between these two will be an Iwasawa main conjecture phrase in terms of these classes. Okay, so. Okay, but restricted to the cyclotomic line. Okay, so these are two variable cohomology classes living up here, but now we restrict them to this cyclotomic line. So this is a projection of VF alpha to H1 Iwasawa, K infinity plus TPU. Okay, so we get these links. Okay, and now I have all the ingredients I need to at least give you a sketch of the proof of Theorem B. Oh, by the way, are there any questions? Maybe before I move on. Okay, so
Francesc, there's a question from Ashay.
oh, okay.
Yeah, sorry, just a comment. Like the Bertolini, the Amon Venerucci, the elements are over Q.
The elements are. Is that a question or it's a statement or?
It's a comment. I don't know. Yeah.
Okay. Yeah. So yeah, as I said, it's a related work. So yeah. Yeah. Thanks for the comment. Okay. Any more comments or questions? Okay. So yeah. So now I can give you the sketch.
Yeah, there's one question.
Okay, great. Yeah. Mm-hmm.
This pain into L function is integral. Is it known?
Yeah, actually, that's some of the work that goes into our part of the refinement. So this Perrin-Riou-Pedicle function, it has some denominators, but they are controlled by the congruence number of the new form associated with the elliptic curve. So this Perrin-Riou-Pedicle function that I'm writing is one that I'm normalizing. So I'm multiplying by this congruence number of f to make it integral, and then we need to relate this congruence number to some modular degree that is showing up in another part of the argument. But yeah, the one I'm writing down, it's integral.
Thanks.
Yeah, no problem. Okay, so if there are no further questions, I'll move on to the sketch. Okay, so this might look a little funny, no? Because Theorem A has to do with the anticyclotomic line, and Theorem B has to do with the cyclotomic one, and these almost don't intersect, but they do intersect at the trivial character. Okay, so that's what we're going to explore. Okay, so maybe I can draw first this picture, okay, of this plane, the ZP square. Okay, so one can, okay, so there's two distinguished lines here. One is this, okay, so we can think of these coordinates as being V and V bar. Okay, and then the cyclotomic line would be this diagonal line. Okay, so this K infinity plus. And then there is the anti-diagonal. Oops. See if I can go through here. Well. Okay, so that's the anticyclotomic line. And what we're going to do actually is work with an anticyclotomic shift of the cyclotomic line. Okay, so we're going to work along this line. So that's why I've been taking this 2 by alpha. Okay, and we're going to use this intersection here as a way to transfer information between Theorem A and Theorem B. Okay, so our Theorem A is applying to this line, and then we're going to look at this point to get information about this line, and then finally we're going to get over here. Okay, so let me tell you how the argument goes. Okay, so okay, so the first thing is we're going to use the fact that these classes, these Benson flat classes, they form an Euler system. Okay, so and more precisely, this cyclotomic projection forms a cyclotomic Euler system. Okay, and that will give us a divisibility in this main conjecture I'm mentioning here, which then we can transfer to a divisibility here. Okay, so by Euler system argument, for BF alpha plus, that gives us that. Okay, so this everything now is cyclotomic here. Okay, so this module I'm writing, we can show is lambda torsion, and we have this divisibility of characteristic ideals. Now, well, in order to apply, for the Euler system machinery to give you something, you need to know that your Benson flat class is non-trivial. And that's where we use our arrangement. One of the uses we make of this arrangement over here. Okay, because this non-vanishing together with the reciprocity law, the second one we wrote, will guarantee that this class is indeed non-zero. So it gives us a non-trivial input to the machinery. Okay, and because we are in this residually reducible case, a priori, the divisibility that you get from this argument is just in lambda with P inverted. But with some congruence argument, together with that Woodbridge refinement of Kato's divisibility, we can show that this actually holds integrally. Okay, and that's another key to everything. Okay, so we have this divisibility in lambda. Okay, so let me give a name to this characteristic ideal. Call it F alpha. Or F alpha will be a generator rather. Okay, so on the one hand, we have this divisibility, but on the other hand, our theorem A, twisted by alpha. Okay, so specialized at t equal to 0 and twisted by alpha. Okay, plus these explicit reciprocity laws that I draw gives the following. Okay, so it gives us that when we evaluate this characteristic power series as a trivial character, we get equality, okay, up to a p-adic unit. Okay, so we get this equality. And when we took this alpha at the beginning, it said that it was sufficiently close to 1. So first to have this non-vanishing, but also we can take this alpha so that this value over here is non-zero. Okay, and that's something that we can arrange, again, by a congruence argument together with this relation over here. Okay, which will allow us to use Rorlich's non-vanishing results to arrange for this second non-vanishing. Okay, so this is ultimately possible by Rorlich. Okay, but now it's a simple piece of commutative algebra that if you have this divisibility and equality at a point and these values are non-zero, then you get equality. Okay, so basic cumulative algebra then implies that f alpha is actually the same as the ideal generated by this p-adical function. Okay. All right, but now we have this alpha here, and alpha is congruent to 1 mod p to the m. So it's not very hard to show that this characteristic ideal is actually congruent to the characteristic ideal for the thermal group without the twist. And also, in fact, easier, this thing is similarly congruent to the same object without the twist. Okay, so these congruents are all mod. Bar pi to n. Okay, so using the congruence that alpha satisfies. Okay, but now once you have this congruence mod p to the m, you can, well, it follows from this congruence that the mu and the lambda invariants will have to be equal. Okay, so this implies that the characteristic ideals are, the Iwasawa invariants are equal, and we have a divisibility. Okay, we have a divisibility from the Benson flag argument that apply to, sorry, yeah, I'm applying to this. Okay, so these two are they have the same Iwasawa invariants, and we have a divisibility, so we get equality. And now you can use Kato to separate the main conjecture for E and its quadratic twist. Okay, remember that each of these sides will decompose as product of two things, one for E over Q and the other for the quadratic twist over Q. Okay, so we use Kato to separate E over Q and its quadratic twist. Okay, so you get that the characteristic ideal of E bullet over Q infinity is generated by the Mazur and Swinnerton layer p-adical function. And now the last step is just using the well-known fact that the main conjecture is invariant under isogenies. Okay, so if you have it for E bullet, you have it for our originally. So this is by invariance under isogenies. Okay, so that was something shown by Ferran Riu sometime in the 80s, that both sides of the main conjecture change in exactly the same way. The only thing that changes is the mu invariant, and they change in exactly the same way as you change your elliptic curve within an isogeny class. Okay, so what does it say? Mazur's main conjecture holds for it. Okay, so for the first two lectures, I'll be finishing 5 minutes late, so maybe it's fitting if I finish now 5 minutes early. So yeah, I'll stop here. Thanks very much for your attention.